Hi everyone, my name is Raghavan Pichai, and I will be going through this presentation on deep dive into EXT4 file system. Thanks for joining in, and thanks to Mr. Aditya for setting this up. And if you guys can just introduce yourself on the on the chat window, that'll be nice, because then I can get to know basically what's your experience, and I basically want to know what is your expertise in file systems as far as concerned, whether you're beginner or like you work on file systems extensively. That will kind of help me when I'm going through the material to to whether to take a decision as to whether I need to go into some conceptual modes, or I can skip through some of them. So with that, I'll start. So you just can put it on the chat window. Yeah, my name is Raghavan Pichai. I have around 30 years of experience in the systems industry, and I worked a lot on embedded systems, and I have worked on a whole set of file systems. And so this particular talk is about EXT4 file system, which is the currently used file system. I think so. I'll just go into the slideshow. Sorry. Okay. So, so the agenda for this particular talk is, we're talking about modern file systems. What is the requirements out of the prevalent file systems as of now, and basically the evolution of the extended file system in Linux. So if you see all these file systems, EXT2, EXT3, and EXT4 all start with EXT. They means extended file systems. So extended in the sense like there's a large portion of EXT2 even in EXT4, and obviously of EXT3 too. So it's kind of a evolutionary file system than a revolutionary file system. And the things have been added as the requirements came in. So we will see how the extended file system family of file systems basically evolved across time. Then, so like I said, since it's an evolutionary file system, we would go from the basics set, which is the EXT2. Then we'll jump on to the EXT3. Then we'll go to the EXT4, and then we will do a kind of a we'll go through all the features, and then we can do a kind of a demo session or a practice session on going through the EXT4 on disk layout, and how to mount it, and what are the various modes, and how do you look at the inodes, and this will be an interactive session, so you guys can stop and ask questions, and if I can answer, I'll answer. Otherwise, I'll take it down, and then maybe via Aditya I can spread across what exactly will be the correct answer. Okay. So before we go into the actual deep dive, because I see a lot of people here saying that they are kind of new to file system concepts. So I think so this will be helpful. Basically, what is the terminology or the jargon that's associated with the regular file system? The basic thing is the inode. Okay. So inode has two flavors. One is the on-disk inode, and there is then in-core inode. So inode is basically a representation of a file. And in Unix, whole sort of things are files, like devices are files, directories are files, everything is either a file or a process. That is the Unix way of doing things. So so the inode is basically the on-disk. So this particular course, I will not really go into how the file systems are being treated in buffer cache and the block device and all the stuff. This is going to be more on the on-disk representation. So when I talk about an inode here, it's mainly the on-disk view of a particular file, which contains a whole lot of things, like the creation time, the access, then obviously the representation of the actual data that the file holds. That is referred to as the inode. Then along with the inode, you have something called a directory entry. So directory is also kind of an inode, but the directory entry are basically the entries of a particular directory. They are they are the contents of the directory, and these are basically used when you need to traverse through a directory, or you need to go to a particular file. You need to go to the directory entries. Okay. So that's called as a path traversal, path lookup. That is the general term that's used in Linux. Then you have a super block, which is the kind of, the root block. And this contains so a file system is like normally like a tree, and the top of the tree, from there you go to all the directories and then all to the inodes and then the data from the inodes. All that is done by the super block. So which is normally kept at the first block of the, where the block device which is holding the file system. Extends. So normally a file system keeps everything in terms of blocks. So block sector was normally 512, now it's become 4096 bytes. Now a new term that is used is called as the extends, where instead of since files have become very big, you store a whole contiguous set of blocks together, and a contiguous set of blocks is called as an extend. Okay, now you'll see a lot of terms calling them, a lot of file systems as extend-based file systems. So previously it was block-based file systems. They all evolved to extend-based file systems. Metadata is basically, which is not data. So all this information which is, so the metadata is basically what is not data. So basically what I said right now, the inode information, the directory information, the super block, all that is referred to as the metadata. And then you have the journal. A journal is a concept which I'll introduce as a part of this. But this is basically a place where you write whatever, you kind of log whatever the file system operations are before you do the actual file system. That is referred to as a journal. So it's kind of a transaction book, just like you go to a shop, someone maintains, the accounts. It's like the file system maintains what are the various operations coming. That's called as a journal. And FSCK is a kind of a tool that is a bunch of tools which is used for file system checking for the file system validity in case the file system has got corrupt or something of sort. The FSCK kind of stuff is the file system checker that gets used a lot. So we'll go to the next slide. Now we'll first talk of the requirements of the file system. Okay, so file system is like a database, in a very broad sense. And people who come from the database background know about these things called ACID properties for a basic file system, which is basically 4 properties, atomicity, concurrency, isolation, durability. So atomicity basically, like you guys should be knowing, which is with all instructions run or none of the instructions run. Why it matters a lot more in file systems even than more in databases. Normally databases have 2 kind of things: pre-commit, commit, post-commit kind of stuff. Case of a file system, a particular file system operation can cause multiple transactions. For example, even if you're just extending the block by, file by 1 block, it causes a bunch of metadata operations beneath, like what needs to be done. The inode needs to be updated. Okay. Then a whole bunch of, the inode characteristics, like the create time, the access time, everything needs to be operated. Then in case, you have accounting for that particular file, like things like quota or, the file system, the size properties, although all those has to be operated upon. So along with just writing the block of data, there are a whole sort of other things that needs to be updated as a part of writing to a particular file. Okay, and all these things are invisible to the user, but they need to be committed. Otherwise, your file system is going to be in an invalid state. So atomicity basically says that all the operations, including the metadata operations, they need to be run. When you say file system operations committed, everything has to be done, and then only you say that it's basically done. Else, you can have parts of a file system which are out of sync with each other. Then concurrency is basically you are going to have transactions which are running in parallel should run as if they are running in serial. And again, file systems, this is a very, very tricky thing because normally a lot of operations are kind of, they stomp on each other. Okay. Like for example, you're deleting a file and then you're creating a file in the same way. These kind of things keep on happening, right? And you need to make sure that, when these 2 operations are running, it is as if they're running one after the other. And you need to make sure that the proper error communication is also sent to the user. Yeah, otherwise you could have, each transaction, if they're stomping on each other, then you could be returning success to the user, but the state of the file system could be somewhere in between. Then the third thing is isolation. So the results of one operation should not be, exposed till the commit is basically done. So if you're going to have 2 operations which is running in parallel, normally what happens is the operations basically they get done in code, that is in memory, and then they get committed. So the middle of whatever the operation is that's going to be in code should not be seen by that another transaction, which is again very, very tricky. So the file system basically has to look, if one transaction is running, it's a bit way, and another transaction comes, it needs to figure out the dependencies between these two operations. And then it has to figure out whether this operation can run while this particular operation is running, or it has to stall that particular new operation, and then it has to wait till this transaction is done, then it needs to admit the new operation. So all these kind of checks needs to be done by the file system while admitting new operations itself. And the fourth thing is obviously very important is the durability. That is, the effects are not lost until the commit is or after the commit is done. So this is very tricky because many times what happens is you commit to the user, then you reboot and power crash, and whatever the operations are done, they are in limbo, right? So enterprise file systems, they need to make sure that all these four characteristics are honored by the file system. And one obviously important thing is, which comes as a part of the durability, which is very, very important, is especially that you need to honor the return condition to the user. If you're saying it's a failure, there should be no reason why the file system operation should be done, or even portions of the file system operation should have committed to this. Similarly, if you say it's been successful, there's no reason why any portion of the file system operations could not make it to this. Okay, so that is, you have to honor the return condition to the users. So these are all given things as far as the file system operations are concerned. And obviously the file system also has to take care of things like, so these are the software-ish characteristics. You have the hardware characteristics, which is handling hardware failures. So file systems basically run on, used to run earlier on cranky hardware. Nowadays, at least the hardware is pretty good. So you need to make sure that, things like whatever the hardware failures are happen, that it should be taken care of. And nowadays the file systems have advanced features, okay, that is almost taken for granted. Things like snapshots. So snapshot is a point-in-shot representation of the file system. So this is basically used for, in case if a file system is in a bad state, you kind of revert back to one of the snapshots. And normally all file systems nowadays have snapshotting that happens in minutes, hours, days, and years, and all kind of stuff. Then deduplication is a mechanism by which, especially now with all the social media, you're going to have a case where the files blocks might have the same content. So you don't want to keep on storing the same data across multiple, across multiple files or even across multiple snapshots. So deduplication becomes very important. Compression, obviously, you need to compress the data if it's not actually compressed. And clustering is basically you need to access the file system from multiple nodes, or you need to creep itself the file system across multiple, storage storage modules which are across a network. So that's also a very important thing as far as the file system is concerned, especially from the cloud offerings and all the kind of stuff. Clustering has also become a very important part of the file system. So this is in a nutshell what is the requirements from the file system. Any doubts till now? Okay. Now, so why we are talking about this is, like I said, since EXT is an evolutionary file system, a lot of things have changed from say EXT2 to EXT4. So we need to figure out what are those changes. So EXT2 was started somewhere in 1996 or something. It started, and so EXT4 now is 2023. So the same kind of extending file systems have been standing ground for last 25 plus years. So a lot of things have also changed in the storage media. The main thing is you have two kinds of storage as of now, but both of them have got used. I'm not talking about tapes here, which is basically used for backup. You have basically usually had hard disk drives, and which have basically changed to the LAN. So hard disk drives are basically mechanical in nature. Basically are those spinning disks which are magnetic, and that it has the CHS kind of format, the cylinder head and sector. And previously the sector was 512 bytes, it changed to 1024. Now we have 4096 bytes. So every hard disk drive also has a BIOS by which you can change these characteristics. And hard disk is basically meant to wear and tear, in the sense like because it's mechanical, there could be cases where your C could not happen because the needle could not be pointing to a particular sector. That happens all the time. You cannot access a particular block. Corruption in the hardware is taken for granted, and that's why you have the technology just called as RAID. RAID is an array of inexpensive disks, which is basically you kind of replicate the data, and then you have parity information. So you can first thing obviously is taken for granted is first you need to detect corruption, and there are ways by which you can use parity to recover back from corruption. But this is a minimal amount of corruption that each RAID level has a minimal amount of corruption and the maximum amount of corruption that it can take care of. So that was taken care by for corruption as far as hard disk is concerned. Then the NAND came, flash basically came somewhere in mid 2000s. Basically, it's non-volatile storage. It acts like memory character as far as the IO is concerned, but basically what happens is even if the power goes, you are going to make sure that the contents is there, so it's storage. NAND is kind of the flash is obviously it is not as bad as the hard disk is concerned in terms of the wear and tear is concerned, but NAND is basically limited by the write and erase cycles because before you write to a particular block inside the NAND flash, you need to erase it. And how many times erase can be done is kind of each flash has a particular number of count to it. So more than that, it cannot be done. So the flash, there is a layer called FTL, which is talking about the flash, which makes sure that it kind of redistributes the data. So it kind of converts the physical to a logical mapping to make sure that too many erasers of a particular block doesn't happen. It keeps on moving the physical block to, and then it provides a logical representation to that. So as far as the external guys is concerned, he's thinking that writing to a particular block, but the block itself keeps on moving. So this is called as the wear leveling, and the FTL takes care of that. So as far as connectivity is also concerned, you had initially when you started in late 90s, it's all SATA, which is serial ATA. SCSI became very popular, okay, which is now almost a de facto thing as far as it has a lot of advanced features such as parallel IOs and locking and all that stuff. Now we have NVMe, which is more for memory fabrics. So flash arrays for NVMe, which provides extremely high IO, now has become the next thing that's being talked about. So when EXT started, it was all hard disk drives, and now in EXT4 we're talking about NVMe and all those kind of things. Now, as far as next thing is what is the kind of evolution of the storage, content itself. Initially, when the storage subsystems were started, they were basically meant for the desktop environment. Okay? Whereas servers were focused mainly on databases, because initially when Linux started, it was either desktops or it was servers, and servers were mainly databases. And storage subsystems, desktop is mainly files which are like medium-sized files and all kind of stuff. Then later, what happened was the explosion of the multimedia content. There are a lot of big video files coming in, streaming files and all the kind of stuff. You need to do seek somewhere in between, randomly you need to do a seek and that kind of stuff. Then you had objects which came to landscape, because especially with respect to all these HTML content, all the stuff. So basically, you had very, very small files, but a huge number of small files. That's basically what is called as the objects. Okay. Then you had the later content, especially after 2010, you had VM images. So basically, you had these big images that are actually VM images, which is as big or even bigger than a database, because the VM itself could be stored in a database internally, and they need to be stored. And these VM images are very tricky because they are they are called thin files or sparse files, because you really don't know how is the distribution of the data across. For example, if you're talking a video file, the size means it's like fully packed from beginning to end. But these VM images are like, big hard disks by themselves. You are kind of logically representing them. So then you don't know where the filled sectors are, where the unfilled sectors are. So you need to kind of maintain them. And these were like huge files. So when starting out, the sizes of the file VM images now goes into terabytes, and the file system has to make sure that it scales from small objects, huge numbers, to these big, large, huge files. There's a concept that's being used in Linux. So depending upon this, this is my classification. There are three kinds of file systems that that as of now we can classify. One is a very basic, EXT2, very basic file system. That is it. That's what a file system does, which is in terms of the metadata and other stuff. But there is really no inherent intelligence in this to prevent any kind of recovery, those kind of things, and even things like software race conditions and all the kind of stuff. They needs to be solved on a case-to-case basis. For example, we'll say we are moving a particular file, from one directory to another directory. How EXT2 solves it? It creates the new entry in the target directory, then it goes and removes the entry from the source directory. Because if it does the opposite way, then there's a very good chance that the user would have seen the result committed, but when you see the entry is still there in the source directory. Now, at least with this, your error checking tools can kind of figure out that if you create the new directory in the directory in the new area, and it looks at the access time, the create time, then it knows that there is if it's a duplicate entry in the source, it goes and cleans it off in case of a unclean shutdown. So all these jugards, get done. There's really no thumb rule to this. On a case-to-case basis, you need to figure out what are the various race conditions, what can happen if if the power goes in between a transaction, and so all these file system checkers do all this kind of stuff, which is very unclean, but that was how the old file systems were. Then in between, you have these mid-level file systems with kind of error resiliency built in. So they basically use of journaling to prevent unclean, the file system. So we don't have these kind of race conditions to be handled, because the journal kind of tracks which are the list of file system operations, and it allows up to scale from smaller files to huge files. So that's where EXT3 is, EXT4 is XFS. These are some of the commonly used file systems. They're not the best in class for enterprise, but they are okay for embedded file systems for desktop and for certain class of enterprise file systems. For enterprise level, you have ZFS, which is a common file system. There's something called the BTRFS that was also pitched in for enterprise, but that did not fly through because it was very buggy. These have advanced features. So there's something called the copy on write. I think you guys know about copy on write in memory. A copy on write as a file system is concerned is, it's like whenever you go and change a particular file system block, it allocates a new block and writes the contents to that. So you have basically a logical blocks which are given to the actual file system, but actually the logical to physical mapping is done by this cow layer. Okay. The advantage is with this, what happens is immediately going to have snapshot. You don't have deduplication built in, because what needs to be done is you need to maintain a hash for each of the blocks. If the hash is already there, you just go and give the same block. If the hash is something new, you need to know that a copy on write has to be done. And once a copy on write is done, you kind of stitch the entire file system all the way to the super block. So that way what happens is a new file system layout is basically done, and immediately the old file system becomes a snapshot. So the copy on write is now extensively used in file system ZFS, and it provides this. And along with that copy on write, they provide clustering. So either limited clustering in the sense like across nodes, where your file system is sitting on one particular storage box, and you can access it across. Sorry, I'm getting some questions. What is okay? Subhajit Pandey is asking, can you tell something more about SATA? SATA is kind of a serial ATA interface. It's kind of a slower IO subsystem by which you kind of go to. It doesn't allow for parallel IOs to be done. It goes to a particular sector and then reads the data and then sends it back. That's in a nutshell what a SATA basically does. So next question is, what is unclean file systems? So like I said, a file system, suppose if I'm having a file system. So basically what happens is, when you write to a particular file in a particular file system, a lot of the data doesn't go immediately to the hard disk. Okay, there are multiple layers. So basically you have the hard disk, and before the hard disk there are also caches. Okay, they are basically, because since the hard disk is slow, right, you're going to have caches in front of it. So, and along with it, you're going to make the file system layer itself in Linux kernel is going to make sure that in case the data is going to the actual hard disk, it tries to consolidate blocks which are close to each other and then sends it to the block device driver. There are some IO schedulers which is called as the elevator algorithms, which is done by Linux. Basically what it does is it looks for blocks which are closer to each other. So because the idea is, since you're going to have this cylindrical, this mechanical nature of this disk representation. So basically what happens is, you want to make sure that when you want to write adjacent sectors together. You don't want to write one sector here and then write one sector, because that means to go to the new sector, the magnetic drum has to spin so much. This is not so much of a problem as far as the NAND flash is concerned. This is a very acute problem as far as the old magnetic display concerned. So there what happens is, the file, that's why the Linux, the VFS layer, it kind of caches. So when you write, basically returns even to the user, it has not been actually committed to the hard disk. The Linux VFS kind of caches it together. And then once it figures that there's a bunch of blocks which are close to each other, then it hands it over to the IO subsystem. And that guy makes sure that it bunches this stuff together and then writes to the actual IO. So because of this, what happens is, when the system, and you really don't know what has been written. It could so happen that it has written data and has not written the metadata, or written portion of the metadata and it's not written the data. So in between, if the power goes, basically what happens is, all your in-core representation has also been lost. When you reboot the file system, your file system is basically unclean. You really don't know what has been written, what has not been written, and whatever has been written on the disk, you need to reconstruct it, right? That's what the file system checkers, the FSCK, and all this. Is that answer good enough? Okay. Next question is, could you please give a brief on network file systems, NFS, Samba, and all the stuff? That's a different topic by altogether. Maybe we can do a deep dive on that later. Okay, not as this particular session is concerned. Can you repeat about cow? Okay, so cow is a copy on write. So basically, let me take an example. Suppose you're going to have a particular file, okay, with say 10 blocks. Now you are writing to the 10th block. Now there are two ways. Now if there's a static location, if the file, the 10th block is say mapped to sector say 1000, basically you are going to make sure that in a non-cow file systems, the write to the same 10th block is going to write to the same physical block, which is 1000 always, right? But in case of the cow file system, what happens is, first time you do a write to this 10th block, it is going to say location 1000. Next time you're going to write to the 10th block, is going to a different location, 10,000. Okay, so we are basically going to have two copies of this 10th block. One is a older copy and one is a new copy, right? So the older copy can be treated for snapshot and the newer copy is the present. So when the read of a particular user happens, it always goes to the newer copy. Okay, but the older snapshots and all that stuff, they make use of the thing which is there in 1000. This is inbuilt inside the file system. So as far as the file inode is concerned, it talks about logical things. It says block number 10. How the block number 10 is actually mapped to the physical block, that is managed by the cow file system. And the idea is, once you do this, you are basically the inode structures and all that stuff, the directory entry structures, they always talk in terms of logical, but the actual physical keeps on moving under the hoods. Okay, and with this, basically what happens is snapshot can be done. Now in the snapshot, so whenever you do a write to a particular block, the older one actually becomes a snapshot. Okay, so this is basically what a cow file system basically is. Is it clear? Krishna Sai? Who manages the logical to physical mapping? That is done by the cows. There's a layer below, which is kind of not seen by the file system, that does this kind of mapping. So it actually knows, that has the physical, representation. It knows how many blocks are actually there, how many are free, all this kind of stuff. It's done. That's a separate layer below the file system. Is it similar to page tables in MMU? No. This is a logical one-to-one this thing, but there's nothing like similar to the page, because the page tables in MMU to a total different thing. So this is more of, it's kind of similar to the page tables because it does the logical to physical, but there is more meat there. This is a pretty simple thing as far as the file system is concerned. Major difference between EXT4 and patch, we'll come to that as a part of the EXT4. Now we'll go to the next thing. So first, so now that we got to know what is the evolution of the storage media and the evolution of the storage content, we'll now, so basically, like I said, we start from EXT2. We understand what EXT2 is, then we go to EXT3, then we go to EXT4. Okay. Now EXT2 is basically a very basic file system which is available from initial file days of Linux. So basically what happens is it allows for, like what I said, the basic metadata, the basic metadata to be, to be represented, which has, inodes, super blocks and all this kind of stuff. The directory entries, all these basic building blocks which are required for a file system are basically allowed, are basically, available as a part of EXT2. So EXT2, if you look at the organization of the EXT2, it's pretty simple. Basically what it does is it divides the entire disk blocks contents that it has into something called as a block groups. Okay, so each block group contains inodes and the data blocks. The idea is you are going to store the data blocks closer to the inodes so that your disk access, seek time as far as this disk are concerned, is minimized. So you're going to make sure that the blocks which are belong to the same file sit within the same block. Okay, so this is just for making performance better. And the block groups also gives a mechanism by which you're going to have, the metadata like super block or even the inode information gets distributed across these block groups. Okay, so along with that regular, inode, super block and all stuff, this is one extra metadata that has been introduced by EXT2 to make sure that you have a better performance and then you have better redundancy as far as this is concerned. Now, and there is going to be a block bitmap that's going to be allowed inside for, for the free blocks inside this particular group. So you're going to have that block bitmap is going to be maintained by one 4K block. So since they're going to be one 4K block and basically maintain 128 megabytes, of basically 4 into 32K, which is 128K. So and 128K into this thing is going to be 128 MB of blocks. So the basically 128 MB of blocks can be basically accessed by one block group, because the free information within that block group, how many blocks are free, is going to be maintained by one 4K block. So this is what effectively a block group does. So in nutshell, a block group is nothing but bunch of blocks. The entire free blocks is partitioned into different block groups, and the file system is going to make sure that the inode and the file system data blocks are going to be allocated within that block group. But if the block group is got full or other kind of things, it has to go and access data which is outside these block groups, in which case the performance kind of might get impacted. So okay, any questions here in this slide? Okay. Now coming to the actual file representation, okay, in the previous in EXT2. So this is a classic Linux Unix representation. Okay, what's someone waiting? So basically each inode has 4 levels of access in the block. Okay. So this is the inode, whatever you see here, the owner, signs, timestamp, blah blah blah. And then you have thing called direct pointers, single indirect pointers, double and triple. Okay. So the direct pointers directly point to the data blocks. Okay. There could be actually normally 10 of them which directly points. Then you have the single indirect pointer. So basically single indirect pointer is you're going to point a block and that block is going to point to the actual data. Okay. Then you're going to have a double indirect. You're going to point a block which is going to point a block which is going to point to the actual data. And then you have the triple indirect. Okay. So the concept is very simple. The idea was thinking like, we're going to start with small files. Then the files are going to grow. So when you're going to start with small files, you use that. Then you're going to grow, you're going to single. Then you go bigger, you go to double. Then you go to triple. Okay. So this is how the file system, the file itself was laid out in the EXT concept. Okay. Although this works, but if you see, this brings by its nature itself a whole set of problems. One thing is it is not real time. Suppose if you're going to access one block which is at the fag end of a large file, I might have to go through 3 steps of interaction. Right? For a file group which is at the beginning, I need to just go through no interaction. Then there's going to be a whole set of metadata usage, wastage. Right now, if I'm going to access 3 levels of blocks, I need to keep metadata for the first level, the second level, the third level. So although I could just be using one entry, I could just have one block at the end of a huge file, and that I need to maintain the single and the double and the triple and all that stuff. Whole set of metadata usage. Okay, and general file system thumb rule is more the metadata, more chances of corruption, and more useless metadata, more chances of more useless corruption. So you'll end up, the file system checkers will be checking for useless things, and you'll be caught in those kind of things. So although this kind of was okay, but this is not a good way to represent actually files. But this was the way the EXT2 files were represented. Any doubts here?
Yeah, so can you repeat the reason for why it's not a good?
Can you chat your question? I could not hear it.
Sure.
So voice is getting low. Why do you say it's not a good scheme? Okay. See, it's not a good scheme, like I said, because first of all, do you agree that it's not real time in terms of if I access a block at the beginning, it goes through only one level of interaction. When I go through a block at the end, which I need to go this triple interaction, if a file system is large, okay, I need to go through 3 levels of interaction. So your woe of accessing the file block is really not constant. It varies as far as file is concerned. Your size goes, and actually the problem is as the file grows larger and larger, this problem becomes more acute, right? So, which is really not a good way to represent files. And like I said, second thing is because the metadata wastage is very huge. Assuming that you have a very, very sparse file, assuming that you got a very huge VM file, which goes into gigabytes of memory, okay, which has a lot of holes. So you have, say, some 10 blocks at the beginning. You access them via direct pointers. Now you've got one block at the end. You don't know really how the file system actually is created that particular VM or how it's maintaining the VM. Now for accessing that one block, I need to create one direct block, one indirect block or 2 or 3 indirect blocks. And that will just have one entry, because that first level indirect block is just going to point to one entry in the second is going to point to the third, and the third is going to actually point to one block at the end, right? Now you're going to waste so much amount of metadata, 3 blocks for just pointing to one. If you could have just had a direct pointer, because this is just one file at the end, but you don't know, right? So unfortunately got stuck at the end, right? And okay, it's a big hole file, right? So because of this, there's a lot of metadata wastage, and like I said, more metadata, more useless metadata means your file system actually gets bad. Okay.
Can you repeat the last one? More the metadata, useless metadata?
More useless metadata. The file system, suppose if the file system crashes in between, then basically you're going to, you have to recover from a very difficult situation, and which you could have done it by design. See, this is not by design, you could have had a better file system, but this is by design, you had a bad file system. By the file system checker has to do lot of for work for a very stupid design. That's the way you can see it.
Okay. Yeah, thanks.
Okay. Now coming to EXT3. Now, so EXT3, so is there any other doubts as far as EXT2 is concerned? That kind of wraps up EXT2. Okay, no doubts. Okay, now let's,
yeah. So what's the maximum you can manage with EXT2? The size of the disk, size of the file system, I mean.
File system,
it's sure some few GBs.
It should be few GBs. I'm not very sure.
Yeah, that's another limitation of this chip.
Yeah.
Okay.
Then coming to EXT3. Okay. Now EXT3 is basically EXT2 plus journaling. I've just put it as a very simplified thing. It could have a lot of other features also. But this was the biggest feature. It was introduced in 2.4.50. The basic idea is to have journaling. Okay. Now, what is the goals of journaling? Okay. Now, if you talk in terms of transaction context, like what I said when I talked at the beginning, the goal of journaling is to make sure that the updates to the file system do not take effect until the commit happens. So when you say a commit has happened and you record a commit in the journal, okay, you are basically assuring to the user that this data is always durable, is always available even after the file system has crashed. Okay, this is basically what the goal of journaling is. Why this becomes easier when a journal is put is, a journal is going to be one file, okay, and as when the changes are happening to the file system, you are going to pack all those changes and they're just going to put it in the journal. So random access to the file system, because you could have file systems, the files being operated across various disk blocks, across various metadata. You are making a random workload is being converted into a sequential workload by making sure that you're going to have a journal. So basically what happens is you are going to take all these random writes. If you do not have the journal, they would have just, the disk would have just been spinning. You're just coalescing all of them into sequential writes and you're pushing into a journal. So just by doing a single trick of converting a random workload into a sequential workload, you get very good performance. And you get this thing that since now we can commit off very fast, because now the commits are going to be, writes to the disk are going to be extremely faster because they're going to be very sequential. The writes are also going to come back very fast, right? Once the writes come back very fast, you can commit to the user saying it's done. Later, you can actually dispatch the actual writes that's there in the journal to the actual places. That can happen later. That can happen outside the scope of commit. But once you do the commit, the writes are there in the journal, you rush. Okay, so this is the basic, idea of what a journal is. You are converting non-sequential writes into sequential writes, okay, into the journal. Okay, so the crash basically involves two situations. Either a commit is present or a commit is not present. Okay, so if a commit is present, basically what you do, You don't know whether the contents of that has actually gone to the hard disk, because the crash could have happened between the stage when the commit is done and actually. So you go through those commits and then figure out, oh, this is data there, data not there, data not there. You reapply it. These are called the redo logs. You kind of redo it, redo it, redo it. Is the order of writes to files maintained with journal? Yeah, it is maintained with respect to journal. I'll come to it. Okay. It could be either explicit or it could be either implicit. But if the commit is not there, or if suppose you're going to have a bunch of writes to this journal, but there's no commit footer saying that this commit is done, you can just discard that portions of the journal, because you are really not gone and told the user a success or the results of the operation. So you can basically remove those contents which don't have a commit footer. So rebooting from the crash becomes very easy now. What the mount code needs to do is just look at the last few commits, okay, and then figures out, okay, should I do this, redo these transactions? Are these commits actually been written to this? It goes and inspects. The commit has not been inspected to the disk. It does it in order. So it could so happen that there could be an insert, then a delete. It will first do the insert, then it will do the delete. Okay, whatever the ordering has to be done came. So your question is ordering to the right to the files maintained. It has to be maintained. Okay. But it could be maintained implicitly. In databases, normally you'll have a transaction records, they'll have a sequence number and all this stuff. Here, that way need not to be done. We'll come to that. But in effect, that is kind of taken care as part of this thing is concerned. So rebooting from this thing, you really don't, it doesn't become so much of a problem as far as, checking the file system is concerned. In case of, normally what happens is the file system basically in the super block maintains a flag whether the file system has been cleanly rebooted or not. When you do an unmount properly, it goes and writes to the particular flag. If it has not been cleanly removed, unmounted, it just looks at the flag. Okay, it checks, okay, the flag is, not clear, so it's unmounted. So it will just go and, look at these commit records and then just go and flush them and go and start admittedly user operations. Okay. So what does basically journaling guarantee? Journaling basically guarantees faster mount times after crash. That's what it is. Nothing else. Okay. Does journaling guarantee that the file system is totally intact even after the journal is applied? No, because like I said, so there are multiple reasons for this. Now, what happens is there could be, if you are going to go and commit every transaction to the journal, it becomes very slow. Because like what I said, every file system operation could be bunch of 10 to 15 metadata operations, right? So even if one operation gets returned to the this thing, you cannot keep on setting a commit saying, because the user does not even know what metadata has been written to, right? So you need to basically commit only after the entire operation is done. But even this is very, very slow, because you could have data writing to the same file or to the same directory could be happening at the same time. So basically what the file system basically does is it looks at file system operations which are close in time, and it merges all those file systems operations together, provided they're not independent operations. I'll come to that. So as far as the operations are kind of independent of each other, it merges all those operations and pushes them under one single commit. Okay. So once it does under that one single commit window, then only what happens is the commit basically gets the commit returns to the user. Okay. Now, so there could be still a window, where the it actually kind of takes a transaction. There could be a small window where it sends success to the user, but it is the process of merging these transactions and then doing a write to the actual commit. So during this very, very small window, okay, if the power failure happens, then there could be a case where the file system cannot be intact. If you are going to do commit at every transaction level, then your file system performance kind of sucks. So they taken the middle route here, where this kind of thing is cannot be for the better of the file system performance. They have to allow this particular window where the transactions needs to be merged and then the commit has to be. Okay. And POSIX gives a guarantee by which you need to make sure that you need to return back success. You cannot do a file system read or write. The read or write operation has to be communicated back in time, whether it succeeds or not. It does not keep it in limbo. So if your file system return times is going to be, smaller than this transaction merge time, there could be a small window where, this file system is waiting for the transactions to be merged to then write the commit, and between if the power system goes, the file system can go out of sync. So that way the journaling does not really 100% guarantee that the file system is totally intact. Then the another thing is that there are a lot of caches in front of it, both in front of NAND flash and both in front of hard disk. There are a lot of caches, and these caches are basically what happens is if the power goes off, these caches again will if you're going to make it as write through caches, it's okay, but most of these caches are write back caches. So if these caches basically lose the power, then the file system is obviously going to go out of sync. There are mechanical failures. So that's why people might ask, with the journaling, will all the problems like, you don't require FSCK. FSCK is still required because the nature of this is such a way that with these caches and all that kind of stuff, you need to have FSCK. Journaling kind of makes sure that maybe, your file system was like, after crashes previously to recover it's 30%, chances with the file system too. Now it may be upset to 70 or 80%, right? Still there's going to be 20% window there because of all these kind of things. So file system can be out of impact. Okay, coming to questions. Is a journal of fixed size or does it grow dynamically? We'll come to that. Okay. Is the journaling only for recovering from errors or updates to file systems also happen? No. So any file system transaction flows through a journal. So it's not like it's only for recovering from errors or updates. Any file system transaction goes through the journal, and in case of unclean shutdowns, okay, the journal is considered. Once that is done, the journal is just not looked into by the file system except while committing. You don't refer to the journal for actually doing a reading or anything of that sort. It is just looked into while it is read at the time of, so let me put it that way. It is read at the time of, mounting after the unclean shutdown. After that is only written as far as the user workflows is concerned. Is it clear? Can older data be recovered from journaling after FS crash? It depends upon, what is how big your journal is and what kind of, normally the journals gets pulled very fast, then this problem. It can be done. There's no reason why you cannot look at the older commit data and then you can look at, all these kind of things can be done with the journal. Nothing wrong with that. What is the overhead of maintaining journaling? Next one extra file, and we'll come to that when we will see the overhead of maintaining journaling. Sir, how frequent are unclean shutdowns? Well, with the mobile devices, it's extremely frequent, right? We just press the power button and EXT4 gets used, flash devices on Redux. So unclean shutdown happens in my opinion, happens all the time on mobile devices. Okay. Do you think it's fair trade-off for every transaction to go through journal? It has the sense like, see, every transaction goes through a journal. Whether a commit happens for every transaction is a question. You don't want to say that I take a transaction, I commit it, then only I say yes, right? That becomes very, very slow. Maybe databases do that, okay? But as far as file system is concerned, that's you should not be doing that because every file system operation gets, spread and interleaved into multiple metadata operations. Does it mean that EXT4 is not a power safe file system? Most of it, no file system is power safe in my opinion, except very few file systems. Let's say the Waffle NetApp file system and all the stuff, because they write everything to NVIDIA. Unless you are going to give a guarantee that your media is power safe, you cannot say that the file system is power safe. If your media is going to have caches, it's going to have a bunch of other things in front of you, or your media is prone to failures, the file system can do only that much, right? So the question that you need to ask is, how much is the media available prone to failures, and how much is the software that's written as a part of the file system prone to failures? Okay. Does the FS have both data journaling and metadata journaling? We'll come to it. Okay. Is the main benefit of journaling to merge coalesce the writes to close locations? Correct. Like I said, it converts non-sequential writes into sequential writes at the beginning, and later does the actual writes. Okay, someone is still waiting. We are in the middle of the session. Okay, so I will have to cover. So this is the actual picture. It could be a bit confusing. So I will walk through this picture. Okay, this is a kind of a flow graph of how the journaling basically happens. So basically, what happens is when at a new point in time, you are going to start a new commit. Okay, so commit is like, to talk about it's like a sequence number. Commit 1, commit 2, commit 3, blah, blah, right? So here, if you see this particular, bunch of operations that are done during this time window, all will go under one commit record, say commit. Okay, so basically what happens during this time, any user operations that are basically done, they will get converted to EXT4 file of handling. So this could, like I said, result in multiple metadata operations and all kind of stuff. Basically what happens is this results in a write to the journal. How it does results in a write to the journal is via this dotted arrows. So basically what happens when you for a regular file system, when you do a write, basically what happens, you read the data from the disk, which could be both metadata and data. You write it. You basically, your buffers lay in the buffer cache, right? You have the BH data structure, if you remember in Linux. And the BH will have a head, which basically points to which is the block device it needs to attach to. Here, what happens is all the buffers will have their modified disk to point to the journal. Okay, so all the dirty data buffers that are going to be created as a part of your file system operations basically create in dirty buffers, which is the regular case, but the dirty buffers don't get attached to the actual files they belong to, they all get attached to the journal. Okay, so this operation results in this operation, implicitly results in this operation, this second dotted arrow it says, all the dirty buffers now are part of the journal. Okay, but they are all sequential in the sense like all the dirty buffers, so the offsets where they get returned to will be marked so that they're getting returned to one after the next to the next in the journal. Okay, so all these random things are returned to the journal in the sequential. So till like this, multiple operations happens. Okay, now the file system has to be very, very careful in admitting these multiple operations, because here you see all the data is now only input, they're not being committed to the hard disk. Now there could be cases where you could have transactions which could be stomping on each other. Okay, and you need to make sure that those transactions have to be complete. Now assuming that you are these commits have to be again have to be flushed to it, so there's going to be a time for this particular, there's going to be a life for each of these commit window, right? Now assuming that you're going to have one transaction which is almost this guy is like going to almost to the final stages of this commit life, and a new transaction comes which is going to affect one of these other transactions. You mean to say it's dependent on one of these transactions. Basically what this operating system, the file system has to do is it has to stall that new operation, because it's a dependent transaction, right? It has to stall that new transaction and push that other transaction into the next commit. If there is not going to be a dependent operation, it can still allow it as a part of this commit operation, get it fully done and push it. So all these kind of manipulations has to be done by the file system internally to make sure that a bunch of n commit operations, they are all merged together and they go into one commit operation. So this commit n means that all the dirty buffers, okay, that have been attached to the journal, once they get flushed to the actual journal, then you are going to basically say that this commit is basically. So this window is what I said is a window by which the user can get a success, but if the commit gets actually done, this window is a case where you can still have a error, but that cannot be that has to be taken into account because you want to merge these transactions. If I make this commit as a part of every transaction, so assuming that I got a commit here, I got a commit here, I got a commit here, then the problem goes away. But you see how much of complexity it brings, because it means that everything I had to flush it. If you're going to merge these transactions together, then you get that other problem, but you're going to coalesce all these transactions together. This is how EXT4 basically. So coalesces a bunch of transactions into one commit. That's a committer. But remember here, your actual buffers are not returned to the actual locations. They are still being attached only to the jump. Okay, but what the file system does is once this commit n is done, it immediately opens the next commit window and starts allowing all those operations. Okay, the actual buffers gets returned to the actual location. That is done using another operation called checkpointing. Okay, what basically checkpointing does is basically looks at which all of the operations are falling under commits which all are not being written to the actual location on the disk, it goes and then writes those actual locations on the disk, and then it marks that particular record saying that it has been checkpointed. So once a journal has commit record has been checkpointed, that means the journal record can be thrown away because it has been returned to the actual on disk also, and it's of no use as far as this particular thing. Even after the reboot is concerned, you really don't have to bother about it because you know that those contents are actually being written. You don't have to do a redo of all those transactions as a part of the commit. Okay, so there are two parts as far as the operations are concerned. One is called as a committing, which advances, the journal records, and one is called as a checkpointing, which kind of throws away that. So one, if you say that commit is like the head, it moves the head, the checkpointing is like the tail. Okay, and if you see checkpointing is slower because this will have to write to the actual location. So this is not sequential data, right? So this is where it will be much slower than actual what the commit is. Suppose you're going to say 100 buffers is written as a commit takes n number of seconds. Checkpointing of the same 100 buffers to the actual location might take 10 times or 15 times because all this is sequential. So checkpointing by design is meant to be slow, but you are not bothered about it. Checkpointing is like, slowly the commit will move the heads of the journal very fast. Checkpointing slowly is moving the tail, and at some point, the head is going to be away from the tail, making sure that you're going to. If the checkpointing doesn't get, then obviously what happens, the journal is going to get full, right? You need to make sure those records have to be those data buffers actually get returned to the home locations, right? So this is the two parts of the operations, the commit and the checkpoint. Is this clear? What does the dotted lines represent? There are so many dotted lines. What dotted lines are you talking about? Okay, let me explain the dotted lines. See, this bunch of dotted lines is the IO that goes to the, the buffers have been written to the journal. Okay, when the commit basically, when the operation basically gets, to be written to the journal, this stuff basically says that the blocks have been written to the journal. They now belong a part to the journal. Okay, this is later what happens is, as a part of checkpointing, this dotted blocks basically say that the blocks have been written to the actual file location. Okay, whichever the actual file it belongs. Suppose you are going to say, I'm going to write to an inode of say block 100 at a file location of 20. Okay, this second thing is actually going to go and do that actual write to that block number of file at the inode of block file at offset of 20. And this third thing is, this guy is now returns. So as a part of checkpointing, this guy goes and figures out as all the data buffers which have been as a part of this have been returned, because that also it does it in parallel, right? You do not do it sequentially. It issue those writes, wait for all those writes to come. And once it figures out all the commits writes have been returned to the actual home location, it marks a checkpoint. So that's what these dotted lines means. I'm sorry if it is because it's my own figure, so maybe we should have put different kind of colors or something like that. But this is what it means. Any other questions?
Is memory cache for data buffering that we are going to write to the disk?
Is there memory cache for data buffering that you need to write to the disk? Which memory caching are we talking about? Like the VFS cache?
The one after the journal in the picture.
Yeah. This is when I say memory cache, these are the in-core buffers.
Okay.
They are not, I should not call them, okay, it's stupid. It's a wrong term from my side. I'm sorry about it. It's not memory. Okay, I should not call it cache. It's in-core buffers. Let me correct it. Okay. It's the in-core buffers. I wrote it wrong.
Okay. They will be in the main memory, right?
It'll be in the main. Sir, where is the journal stored on which persistent will come? But is there any doubts as far as this flowchart is concerned, or guys do not understanding what commit does, what the checkpointing does? Is it clear? Okay.
Yeah. One question, Raghav. So, can you say that a commit will have only non-conflicting transactions? a particular
that, yeah, or if it is a part of the transaction, the dependencies have to be taken care of.
Sorry, can you repeat that?
The dependencies have to be taken care of, right? So
Okay.
if I'm going to merge the transactions together, like I said, you are kind of moving a file from one directory to another directory, or you are deleting a file, then immediately creating a file. Those kind of things, right? It has to be taken care, right? If you're going to put them together, then actually the file system can be very smart. If it is going to be deleting and removing the file, it can, instead of making the two separate operations, it can just go and change maybe say flush all the data buffers and change the create time of the file. It can do all kind of optimizations, right? So,
yes.
But it depends on the how clever the thing is. But it has to figure out ultimately that there are transactions which could be stomping on each other, right? That amount of visibility that this layer should have. Otherwise, it becomes difficult when you merge the transactions. Okay. Are committing and checkpointing periodical? Correct. They are very, very periodical. So the committing should happen very fast, actually, in the sense like you cannot, what is that? Because you want to make sure that because of this transaction batching, you want to make sure that you really want to commit to the journal as fast as possible, but not too quickly, but not too late also, right? Because then if the journal blocks builds a lot without committing, and then this thing, all those ops will be thrown away in case the thing got rebooted in between. So you're basically lost all those transactions. So you should write to the journal at periodic intervals. Make sure that you have enough amount of wheat that needs to be written to the journal. It has to be done. You should not write it very, very small amount of data also. And you should write it pretty fast also. Checkpointing also has to be done. Like I said, the next figure will explain that. Basically, checkpointing means freeing the journal. So if you're not doing checkpointing at a frequent interval, your journal is going to go full in size, and you're going to come and hit the condition where the journal is full. Okay. So checkpointing also has to be done. Committing also has to be done. And there are threads within the Linux kernel that will spawn, a checkpointing or committing in case it's not happened for a future.
Sir.
Yeah.
Hello. Sir, I just have a doubt here. So definitely a journal comes into picture only when there is an unclean shutdown or something happens. So that definitely means this journal has to be placed in some kind of persistent storage where we don't lose the data, right?
So correct.
So in that case, why are we writing again into some persistent storage where we could have directly written onto disk or maintain something like this? I mean, I just have that class.
Sure. It's a very commonly asked question, and it's also very criticized thing that here what happens is the journal in EXT4 is maintained as a part of EXT4 itself. So it's because what are the two ways? Okay, one thing is you could write all these journals into a separate partition, for example. Right?
Correct. Yeah.
But if you write to a separate partition, you're really not, because that also has to be maintained, right? In the sense like the same things what can happen here can also happen there also, right? Because ultimately everything. Best case what I can think of is you write the journal into NVRAM. Okay, that is the cleanest way of making sure that your file system is the best. Because when you write to NVRAM, you're making sure that the journal, which is the heart of recovery, is always intact. Okay, but very few file systems do that because NVRAM is very costly. You cannot mandate saying that I can build a file system only, use NVRAM, right? That becomes not all of us, or not all of us. And the second thing is, there's only very few amount of data that can be written to NVRAM. Okay? Certain file systems like Waffle and ZFS, what they do is they don't write actually the buffer to the NVRAM. They just write the records, saying that this has been changed, it has been changed, and maybe the data they have to obviously write it. But here what happens is, we are actually attaching all the data buffers to the journal, because you don't have the the leisure of NVRAM. The thing is, okay, instead of maintaining, writing, I'm doing a write here, I'm doing a write, just put everything into this journal and then doing it. So this is really, you're keeping your golden records inside the same failure media. It is debatable. That's a way to start. It's a very valid question, but that's a way to start.
No, one thing is, if you keep it in the separate partition, you don't need a file system to manage that partition, right? It's just the journal data which is there.
Yeah, but see, the normal thing is This thing itself is maintained something called the JBD, which is called the journal block disk. It's a separate layer beneath the file system. But ultimately, your block device doesn't get exposed just like that, right? There are certain ways to use a block device and certain ways to manage a block device, and that has to be done, very carefully. It is not something that that can be exposed out generally like that, because it has to go through a particular bunch of VFS layers and the block device layer. So it's not very easy to just say that give me this and I can write it to this particular block sectors on this. That's not the way it works.
Okay. And see, the performance is going to be good on as long as the checkpointing thread doesn't run for long periods while the commits are happening, right? Because the commits are going to be sequential on the journal. So you'll get good performance only if the checkpointing is not going to interfere in that.
No, checkpoint is not going to really affect the commits, because basically what happens is the checkpointing is going to just go and say that this commit is basically done. So the IO performance of checkpointing and the IO performance of committing are totally different things.
Correct. They are different. Yeah. Go ahead.
So basically, checkpointing, what it does is it frees the journal records, right? So how much time the checkpointing takes? Bad checkpointing, like I said, can lead to journals getting filled. That's all.
Sorry, can you repeat that last one? Bad checkpointing?
Bad checkpointing in the sense like very IO intensive checkpointing can lead to your journals getting full.
Correct.
Right? That's what a checkpointing can do. But the checkpointing really does not have control, right? Because what kind of non-sequential data it has to do, that it does not have a control.
It doesn't have any control, yes.
It does not have any control, yeah. Okay, now I think so we need to hurry a bit.
Yeah.
Now this is the next thing is the journaling in details. Again, my own figure, so it could be problems here. Just if you figure something like this, memory cache, point to me out, I'll correct it. So if you see, this is the basic workflow. I just made this pretty simple. This is your journal, okay? And what you see between these two non-dotted blue lines is one commit record, okay? And you have every journal have a header, okay? This is in a fixed place. The head of the journal, the tail of the journal, and every commit will have a commit number, like this, right? Now, whenever a commit happens, this highest commit number keeps on getting, incremented. We say that this is a new commit, and there should be one more thing, which is the commit which has been last checkpointed. I think so. I forgot that. That also is to guarantee. But basic what happens is, if you see, the commit will keep on creating this new, blue lines, and the checkpointing will keep on deleting it. So the commit basically advances the head, and the checkpointing basically advances the tail. Okay. If you advance the head, basically what happens, your log comes to. If you advance the tail, what happens, you're freeing the log. Okay. Head is equal to tail. There are two conditions, right? Either the log is full or log is empty, right? Initially, log will be empty, but once your head becomes equal to this thing, that means tail. That means your checkpointing is really not run. Your journal is actually full, right? That means you have very, very bad checkpointing, or your commits are too quick and they have too much of incoming data. Then what you have to do is just make your journal file bigger. Okay. But this is basically in nutshell what the commits do and what the checkpointing does. Okay. Now there are three journaling modes again, okay, that will affect the size of the journal. This is provided at the mount time option. One is called the write back, okay, ordered and fully journaled. Okay. Now write back is a mode where we are writing only the metadata to the journal. You are not doing anything else. You are not attaching your data to the actual journal. You are just writing only the metadata. Let's say someone asked in the previous slide what gets written to the journal. Does data get written or metadata gets written? It depends upon what is this particular modes you choose. So the EXT4 gives an option to the user to choose on three modes. In one mode, it says, I will always write only the data. Sorry, the metadata. That is called the write back mode. I really don't know what is the reason they call it a write back mode. It doesn't make any sense, but that is the mode they call it. Okay. The other mode is called as the ordered mode, which is the default mode. So in this ordered mode, the explanation that's given is kind of strange, but it also makes sense. Basically, what it says is, when you are writing to any particular file, make sure that the file data blocks are basically flushed before you write to the actual metadata. So the idea is, when you reboot from a failure, when you come back from a power failure, You're basically making sure that your at least your data is is consistent, and you can build a metadata from there. I think so. This has been basically created for things like VMs or databases, right? Because data is also very important along with metadata. So they are given this kind of option where you can say that the commit will wait not only for your metadata to be written to the journal. The actual data is to be written to the actual files. It's not to the journal. The actual data has been scheduled to be written to the actual files. Then only basically what happens is this guy is going to say that the success is written to the user. Okay, so it's lies somewhere between metadata writing and writing the full data, okay, to the journal. The third mode is the fully journal mode, where you're going to attach your data buffers also to the journal, which is the most costliest mode. Suppose you are writing to a particular file, you're attaching all those, that data also to the particular file. Okay, so these are the three modes which are basically given. The middle mode is the default mode. If you don't give any option, the EXT4 is going to come in this particular mode. Okay, so this particular mode is like in between. It's making sure that if you don't have the journal, what would have happened is this particular thing. But as a part of the journal, you're writing even the metadata, right? So your performance is going to be like a regular file system, because for regular data writes, whatever that is going to be done, except that you're going to have crash recovery. Okay, that is done by this order. The best mode, in my opinion, is the write back, right? Where you're going to write only the metadata and you're going to come back. And obviously, the data has to be, you're going to make sure that you are able to reboot from the path failures in case something goes. And so coming back to this question, the journal is maintained in the same disk as a file and maintained with the journal subsystem, like what I said in the previous slide. Okay, so this kind of wraps up on the journal. Any doubts here?
So in the write back case, you journal the metadata and do you wait for the user data to be written, or
no? You don't. You write back data and then you don't wait for the user data to be written. You return back.
Okay.
Okay. Now we'll go to the next. You guys can chat put the questions on the chat window. Now we'll go to the EXT4. I think so. We're really short of time. Can we extend by half an hour? 3:30, is that okay? Aditya? Oh, okay. Okay, I think so. It will go to 3:30. Maybe 3:15 times. Now we'll go to EXT4, which is EXT3 plus scalability. Okay, like that. So someone asked what is the maximum size of EXT to EXT3, blah blah blah. So the EXT4 basically started somewhere in 2004-5 types, right? That was the time when huge number of big files started coming in. And EXT3 was again bogged down by EXT2 scalabilities. So basically the file system size became a big concern. So EXT3 size basically uses a 32-bit block number. This is a global block number that gets used within EXT3 file system. So for a 4KB, so this is 2 to the power of 32 into 4KB, which is 4 gigabytes into 4KB, which is 16 terabytes. So your EXT3 basically with a 32-bit block number, the maximum size what it allows is 16 terabytes. Okay. EXT4 changes this. Okay, it uses the 48-byte block numbers. So you can do the math, and correspondingly it goes up to 1 exabit, which is really huge. Tera, then after that it goes to some P thing, then it goes to E. So it's 1 exabit, which is in terms of 64. 2 to the power of something minus 64. So this is really huge. I think so. They not reach the cases where this thing has been fully used. Another important thing was the EXT4. So you'd say that just changing 30 to 48 does not really mandate a file system change, okay, which is very valid. Main thing what they did was they changed the accessing of the the file system. Remember that picture where they showed you direct blocks, single direct, all that stuff. They got rid of all the stuff and they allowed for XTs. Okay. So if you remember in that particular representation, what I did here. Let me go back to that. Here if you see everything has been operating at a block length. So your block is 4096 bytes. every pointer can point only till 14096 bytes. I'm talking about pointer money data disk pointer. This is not every pointer, these are disk pointers. They're all 4096 bytes, right? Now, basically what happens is, now you have a case where, like I said, you are going to need to treat sparse files. You need to treat files which can have data which are clumped together, which is a very it's almost characteristic of all VM images. They'll have data which is clumped together, then they'll have a huge hole. Then they'll have data clumped together, have a huge hole. And where the holes lie and where the data are clumped together, no one knows of, because it depends upon the operating system which the VM is representing, right? So you need to have a mechanism by which, first of all, you need to access multiple blocks which are sequential, okay? Or there are going to be no blocks. Okay, that is one characteristic of VM images, even of databases. That also can happen depending on how your databases are maintained. Okay, so you need to basically accessing block by block really is very wasting time. You want to access multiple blocks at the same time. So that is why I came up with the I talked to you the definition of an extent. That's what an extent is, right? And so EXT4 caps the size of the extent. Okay, it makes it as 2 to the power of 15. That is 32K blocks can be addressed one shot. We'll see how it's addressed one shot. So 128 MB of continuous data can be accessed. When I say it's access, means accessing via the file indirection. I can just say this is my pointer, and from now onwards I need to have 128 MB. Obviously, there's going to be disk. You need to fetch it, that goes to the disk, maybe block by block, sector by sector. All that does not change. But you are going inside this files data representation, all this stuff becomes easy, because I just need to go once, say, okay, this is the amount of data, it's sequential. I can do now, I can do faster lookups. I can do prefetches, which is again very characteristic of VM operations. An operating system, when it's fetching data, it will always fetch next block, next blocks, next to next block, right? That's how the program is laid out. And for a sequential program, it needs to take the next blocks and blocks, which is a VM characteristic payload, right? So it can do a whole set of prefetches. So all this can be built, information can be built within an extent. So extent addressing becomes an extremely important thing as far as VM images is concerned, okay? And that needs to be addressed. That obviously cannot be addressed with the block thing. And second thing is, this extent accessing gives necessity for a new file structure model when compared to that other ones, because blocks are continuous. Okay, data structure for holding per block information is like I said, the metadata overhead of maintaining the SQL double block. You just need to maintain only two things. This is my block, and this is so many blocks after that. It could be thousands. It could be like 2 to the power of 15, 32K. Till 32K, I can say that this is my number of blocks which are continuous. I just need to maintain only 2 pieces of metadata information. Okay, so your metadata informations are extremely small. And another thing is, extents can have variable size. Right? Now, whatever I said is 2 to the power is the maximum size. There are extents which is even like for smaller files could be 4K, 8K, it could be like big size. So it could have variable size. So ultimately, you have variable size addressing also needs to be maintained. Okay, and
Sir,
like I said,
hello.
Yeah.
Sorry for the interruption. So can you explain what are extents mean in a bit detail?
Okay, extents by definition means more than one block, multiple number of blocks together. Suppose if I say I have a file, okay, I'm going to say I have a file, say at an offset of say 1000, okay, let me the picture, can I go here? No. Okay, let me put it this way. See, assuming that you're going to have a file at an offset of say nth block number. Okay, say the block number file is nothing but a bunch of blocks, right? At say 1000th block number, right? At the 1000 block number, it is going to have 1000 blocks. That means from 1000 to 2000 blocks, the file is filled, right? Then from say 2000, it's a sparse file. Say from 2000 to 5000, there are not going to be blocks because that portion of the file has not been allocated. Then from say 5000 to 6000, the 1000 blocks have been allocated. So you basically have a sparse file, right? From 0 to 1000, you don't have blocks. 1000 to 2000, you have blocks. 2000 to 4000, you don't have blocks. 4000, 5000, you have blocks, right? This is basically a sparse file. Okay. Now this 2000 to 2000, there are 1000 blocks, right? Okay. So 1000, 1001, 1002. Right? Now instead of maintaining an inode information saying I have 1000, I have 1001, and I have 1002. If I just have one inode information saying I have blocks starting from 1000 for another 1000, that means from 1000 to 2000, I have blocks starting at 1000 for another 1000. That means basically you don't have to maintain the information for 1000, 1001, 1002 till 2000. You just have to maintain two information from 1000 to 2000 because all those blocks are contiguous. So contiguous bunch of blocks which can be represented by a file system with only two things: starting block and the number of blocks is an extent. Is that clear?
Yes, sir. Thank you, sir.
Okay, and extents are basically, so sparse files and extents are basically characteristics of VM images. They get to use a lot as well VM images. Okay. Okay, now going to the next slide. Now, so how do you now? So basically, you need to now define a particular data structure that does this. And I will say data structure will be on this data structure, right? Can a single file have different sizes? Very much. I'll show you that. Also. You can have a demo slide where a single file has multiple extents, different sizes. Okay. Only thing, the maximum size is capped. So once it reaches the maximum size, it has to create the extent. But it can have multiple sizes. So we'll see how an extent is basically constructed using the something called the B plus tree. And before going to B plus tree, there's something called the B tree, and before going to B tree, there's something called the MA tree. So I thought I'll explain to you guys that so that you get a good concept of the good handle on the concept. So all of you, I guess you know about the binary search tree, right? Binary search tree is this thing here. Basically, you're going to have divide and conquer. Your 30 becomes all the things on the right is going to be bigger than 30, and all the things on the left is going to be less than 30. And this is how you do a search. This is what a binary search tree is. Now, binary search trees are very good data structures, but basically what happens is in every node you're going to have only one key, right? 30, 50. But if you're going to have a 4K blocks, right, you're going to have multiple offsets that needs to be packed, multiple pointers, right? So instead of having one, key per, node here, 30 or 15, 50, we're going to have multiple of those things. So this is called the MA search tree, okay? So basically, suppose if you're going to have, say, an MA search tree here, for example, it's called as a three-way MA search tree. Can I close the list of participants? I don't think the email is going to come in now, right? I'll close it. Okay. So here, for example, you're going to be a three-way search tree. So each node will have up to 2 keys and it'll have up to 3 children. So if you see, I represented the same thing as a three-way search tree. So you're going to have 20 and 50. So between 20 and 50, you have 30 and 35. Less than 20, you have this. More than 50, you have 60. Okay. So the same binary search tree can be represented in the search tree, except that you are increasing the storage on every node. Okay, which is a characteristic of a file system, right? Because a block need not have to just store one key, it can store multiple keys. So the basic building blocks for both a B tree and B plus tree is a MA search tree. Okay, we're going to have this, and then you need to kind of figure out where does my new. So when I say this 2050, you can think of all these as offsets to this particular file. So it is something like I am accessing. Actually, this should be opposite 1050. To reverse this, 10 is the starting block number. I am having 5 blocks. That's one extent. 15 is the starting block number. I could have 1 or 2 blocks. 20 is the next block. So you can consider all this 15, 10, 20, 25 as nothing but your starting block number of the extents. Is that clear? Now, the question is, how do I arrange this in a particular way such that I fit them into blocks and I'm able to build a tree so that I can access it very fast? The first building block is the MA search tree. So MA search tree is constructed like a binary search tree, except that you're going to have multiple keys in the particular block. Okay. From this, we go to the next building block, which is called as a B tree. From there, we'll go to a B plus tree because the index, the file information, file system, the per file system data that's maintained in the inode in EXT4 is nothing but a B plus tree. So to explain B plus tree, we need to go through these particulars. That's why I'm having these slides. Okay. Now next we'll go to what is called as a B tree, which is a development of this MA tree. So a B tree is nothing but a MA tree such that you can create a new node only if the current node has at least m by 2 children. This m by 2 is nothing but what is the way I told you, right? MA search tree, that is then m by 2 children. And the root should have at least 2 children. and all leaf nodes should be at the same level. These are rules that are given to the MBA tree so that your tree doesn't become very unbalanced. Okay, you know about balanced unbalanced trees. If your tree is going to have bunch of branches, but each branch is going to have only one sub branch, right? It becomes a very lopsided tree, right? You're going, if all the leaves are going to be at the same level or a kind of pretty at the same level, your tree is getting balanced, right? And what is the idea of balancing a tree? Your O of searching the tree, it becomes O of log n, right? Suppose you are going to have a tree which is going to be having 8 leaves. O of log of 8 is 3, right? So you will have to go only across 3 levels, right? If it's going to be 16, it's going to be 4. So if all your leaves are going to be at the same level, you are going through one thing is going to be log of that, right? So your balanced tree will make sure that you have a very deterministic way of reaching a leaf from a node, right? So a B tree is a way by which you're going to have a very, very balanced B tree, so that when you do an insertion or deletion, automatically the tree grows in such a way that all the roots go to the same level, and the nodes will also gets redistributed all the way to the root, so that your searching operations becomes O of log of n, where log of n is the number of leaves. Okay. Now, how does that is done? Let us look at this particular 4-way search tree that I have here and see how the things gets added to this. I'm not talking about deletion here because that's a different thing. Let's try to understand how insertion happens. From this, you get the beauty of the beauty. Now I got 10. Okay, I'm adding 10. Now I'm putting 20. And now we have to go through these roots. Can you create so this is the root of the tree as of now, right? Because there are no children. It needs to have at least n by 2 children. So it should have at least 2, because there's only one key, nothing can be done. So 2 keys can be added. It puts 20. Now 40 comes in. Now I'm putting a 40. So see, the 40 comes here. Fine, because it can have up till this thing. Now I have to put 50. If I put 50, basically what I mean is it can have only 3, right? Because it can have up till 4 children. That means it can have only 3 keys at a particular. So it has to split. Now splitting, basically what it does is it will push 1 key above. So it puts 10, 20 here, puts 50 here, and puts 40 above. Then a 60 comes, which is this. Okay. Now 60 will go, 50 all has space, it puts 60 here. Now a 70 comes. 70 it puts here because it has space. Now 80 comes. Now 80, this has to come here, does not have any space. So basically what it does, it has to split this. So what it will do, it will put 50, 60. It can put 80, it puts the 70 above. Okay. So here, so what you see here is, as and when the tree becomes full, the tree grows like an actual tree, it goes bottom top, right? Because what you find in the tree, first you find the roots, then you find the barks, then you find the nodes and leaves, right? That's the way the actual, although the representation, you have leaves here, this thing. But basically a tree grows bottom top, right? It goes from the bottom to the top. The B tree grows from the bottom top. So all your leaf nodes are getting constructed first, and then the keys keeps on getting. So your depth of the tree becomes more and more as your tree becomes bigger. Okay, that becomes evident from this. Now let's say now you put 30. Now 30 comes here, it goes to 10, 20, 30. Then you got 35. Now 35 cannot come to this. So basically what this, it splits this. 10, 20 comes here, 35 and 30 comes here. Now your 30, 40, 70 comes here. Then 5 comes here. Now 5 can be accommodated here, it puts it here. Now let's look at this 15, which is very interesting. Now if 15 comes here, it cannot get accommodated because you're already filled here. So basically what happens, it splits this. Puts 5, 10 here, 20. Puts 15 here. But once it puts 15 here, this grows. So it splits this again. So the 15 and 30 goes here, 40 goes here, and so on. So here, if you see, it's become fully balanced. You're going to have all the nodes, trees, same node, and the tree is kind of balanced. Although at the level 2, you're going to have, one guy has 2 keys and one guy has 1 key, but still it's balanced because all the leaves are the same. So this way, your tree kind of grows in a very bottom to the top manner, in a very distributed fashion. Same thing even happens for deleting. So just like when you think goes up and you delete it, the level of the tree keeps on coming down, keeps on coming down. Okay, this is what a BT basically does. Any doubts here? Is this figure clear? Or you guys want to?
Yeah, I had. Yeah, one sec. So you said only the data goes into the leaf blocks and the keys can be in the intermediate blocks as well.
No. So when here the keys, all these are the keys. These are, you can map these as the offsets for the for the sparse file. These are like block offset 10, block offset 20, block offset 40. How the data comes, I will represent. That's a part of the B plus tree. This I'm just maintaining the offset. Suppose if I need to go and figure out, suppose if this final representation, I need to go and figure out does data extent at the block number 20 is there or not. What will I do? I'll go to 40. I'll go to the left of 40, go to 1530. I know 20 is between 1530. I'll go and search for all of this. I'll go to 20. From 20, I need to go to the actual data.
Okay.
Clear? So all these, when I mean to say keys, these are nothing but the block offsets of that sparse key. What is the data? The data will be the actual data pointer and the number of blocks. For example, 20 could have only 5 blocks. So at this 20, I need to, what will be the data representation? Data will be the physical block numbers where this 20 is passed and the number of blocks that are contiguous with this 20. That will be my extended representation.
Yeah, okay.
Okay. Can you move to the next slide? Is this clear for all you guys? Any doubts? Okay. Now we'll go to the B plus tree. So B plus tree is actually an improvement on B tree, such that, okay, I have not really constructed that. All nodes are present in the leaf node. So here if you see, this 40, 15, 30, 70 are all nothing but the offsets of that sparse tree what I need to represent, right? What I'm doing is along with this, I'll use the same rules, but I'll have extra space so that all this 13, 7, these things that you see here, right, also will be there in the leaf nodes. Also will be in the leaf nodes. So the 7, 23, 31, 43, and 13, they will also live in the leaf nodes. I'll come to that voice then. Okay. And the pointer to the actual data is also present in all the leaf nodes. So here, what is the pointer to the actual data? The physical blocks, right? As far as the sparse tree is concerned. That will also stay, and along with the number of blocks. That is also going to be staying. That is the data payload for each of the keys. That is also going to be staying along with the keys. So here you have a very beautiful representation. What is the representation? You have this entire tree being maintained as a single linked list as leaves. If you walk through this, you don't have to. If you go to the starting block number, I can go to the ending block without traversing this tree because I have the entire tree as a maintained as a linked list. If I maintain a pointer from here to pointer to here, pointer here, I can just make. So look at, you are going to cat a big file or going to do a dump of the big file. You really don't have to keep on going up and down. You're going to go to the first block and then dump the entire thing using a linked list. So look at the kind of performance benefits that this gives. And second thing is, this is very, very useful when you need to split a block or coalesce. Now, suppose I'm going to say at the second block, I'm going to have, a segment, an extent, say, which is going to have, say, blocks from, say, 1000 to 1500. And 3, I'm having, say, between 1800 to 2000. Okay. Now I'm adding something between 1500 to 2300. What I can do is quickly, I can do that, saying that instead of going, just putting that into, say, modifying 2, saying that now it's become from 1000 to 1500 to 1000 to 2000. I can look at its neighbor. Neighbor is 1800 to 2000. I can coalesce these two. I can make 2 and 3 a single one. You can do a whole bunch of all these jugards by maintaining all this kind of information. What I need to just need to look at the neighbor, because what you're going to do, the extents is basically about looking at neighbors. Can I coalesce with this fellow? Can I split with this fellow? Okay, how do I do that? All this information is made. So this way, a B plus tree becomes a very, very beautiful data structure for maintaining the neighbors information, which is very much for an extents. Okay, along with that, you maintain the data also, right? For each of the nodes, which are not only staying in the leaves, they're staying in the non-leaves also. So we got an entire file system representation. This is what a B plus tree does. And this is how a EXT4 file stays. Okay. Any doubts here?
Yeah, one question. So every file is represented as a B plus tree?
Yeah.
Okay.
I think so. There are some options they give, saying that if you don't want to use a B plus tree and you want to go to the old file model, you can still do that. There's some, IO, some FCNTL call or something like that, which EXT4 allows that. I'm not sure of that, but by default, this is the mode. Or maybe they switch over when file size is some few hundreds of bytes to go to that, and once it goes beyond that, it goes to this. Then it has some kind of policies. Any questions on this?
Sir, how are the extents here? Like you said, for example, 1000 to 2000, it is densely allocated, and 0 to 1000, it is sparsely allocated. So how are we like representing using a B plus tree?
Yeah, so you see each, for example, this 2 here, for example, okay, is nothing but, you can consider, say, I'm building on, let us take very, very simple case, okay, let's not, assuming this 2 is a block offset. Your spy, basically what it says is, your file is not having any file at block number 1. It is having a file at block number 2. That is what this 2 is. Then it's having one block at 2. Then it's having one block at 3. Whether it has fourth block, we don't know. If 3 is just going to be have one block, then you're going to have a fold between 3 and 4 because the fourth is there. And then you're going to have 5. So these numbers that you can see here can be taken as a block offsets themselves.
Yes, sir, but how are we defining this is a particular extent? Like, I mean, so these many number of blocks as an extent.
Yeah, so the count as will be represented. Suppose if you say that, let me take one big block number, say 20, not 20 is too small, 31, for example. Assuming that 31, 32, 33 is an extent. I'm not defining very big, it's a small extent, right? How many blocks are you having? You're having block at 31, you're having block at 32, block at 33. In this data payload for 31, I will say number of blocks is equal to 3. That is my extent information. Starting block, and I need to obviously maintain the physical block number where that is going to also, because these are all block offsets, right? Where is the physical block? Because the physical blocks, how it gets allocated, that's left, it could be on this block group, different block. So what I need to maintain is, for this 31, I need to know the physical block number for the block number 31 and number of blocks which are lying next to each other, which is on this, in this case 3. So instead of maintaining 3 block pointers for 31, 32, 33, I'm maintaining only one information, which is 31, starting block, physical block number, and number of blocks. That's the next. Is that clear?
Yes, sir. Thank you.
Okay. Now, so once you understood this, this becomes very easy. So this is what picture you'll find on the internet. Okay, which is actually very confusing, because first time when I was thinking about this, I was trying to figure out what the hell is this. If this doesn't seem to be like a tree, doesn't seem to be this. Then only I later figure out it's nothing but a B plus. Okay. So here, if you see that, this is what is basically, you have 3 levels of data structures. Okay, they publish this in all the papers. One is the extent header, okay, which is stored in the root node, which is nothing but the depth of the tree. This is your extent index, okay, which is stored in all the leaf nodes. So that is corresponding to this fellow. If you look at the previous slide, this extent index is nothing but these nodes, 15, 20, 70, 40, blah, blah. All that is going to be extent index. What does it stores? That still stores a logical block number, but points to the physical block of the next level. Okay, that's nothing but your B plus. You know, there is your, because from here to here I need to go, I still need to know the physical block number, right? It maintains that. The main meat is this extent file, which is storing all the leaf nodes containing the first logical block, like what I said, number of blocks in the physical block. That is this file. Each one of this is being stored here, and you actually have this. This is your EXT4.
This is on disk data structure.
This is on disk. But this is can be easily mapped to the previous. Okay, got a question. Can there be multiple index? No, yeah, it depends on the depth of the tree. Your tree is like 16 multiple index. Okay, I got the question wrong. What do you mean by multiple index node? You say multiple indexes in a node? Yeah, very much. It depends upon the block. Suppose if a block is 4K and each of your index data structure is 16 bytes, you should have 4096 by 16 bytes block. So many, like how much? 40. 256. So you should have up to 256. Please explain how will the extent tree of depth 2 look like. This is actually depth 2. because all the leaves are starting at this thing, and this is one more thing. So it's actually 2 depth, right? This is actually depth 2. So depth 3, then you'll have one more on top of it. Is it depth 1? It depends on how we consider the leaves as. If we consider leaves as, depth 1, then this is depth 2. Otherwise, this is depth 1. Yeah. If you consider that way, then you'll have one more, one more of this. Suppose if by your definition of depth 2, what will happen is there will be one more block of this index nodes, and there will be one more parent block of this index nodes. That will be depth. Is it clear, Subhajit? Okay. Okay. Now once you understood this, then other things are, there are other additions to EXT4 that needs to be looked into. One main thing is something called the pre-allocation. Now, if you guys know about the fallocate call, which is used in Linux, basically used to create a file that can be used for creating sparse files. Okay, and basically what happens in case of there are 2 kind of files. One is called a thick file, one is called a thin file. VM images or even database images are initially mapped as thin files. In the sense, like, why is it called thinness? You don't put the meat for it. You just carve the metadata and you don't allocate the actual blocks, because you're expecting, suppose, see, normally what these, when you carve a VM image, database image, upfront they want to know whether the storage is available, because these things require 100% guarantee. Suppose if I say, I require a VM image of say 20 gigabytes. I cannot say initially say okay, and then later scratch my head and say that storage is not available. You will have to initially update all your quota counters and all that stuff into accounting into saying that you require this 20 GB has to be taken care of. But you really don't have to actually allocate those blocks of the disk. Okay, the allocation of the blocks of the disk can be postponed because most of these blocks will be contiguous, right? So the allocation can come later because you really don't know. They might require, this 20 GB, they may not require it upfront. This file could grow over days or even weeks or over years. So you can keep on adding storage later also. But initially when they say upfront, you should say whether you should give the commit guarantee saying that whether this thing is available or not. For that, they use this fallocate system. Right, the fallocate system call will basically say, give a guarantee initially itself upfront, and then it will create something called as a thin file. Okay, suppose if I say 20 GB to create a 20 GB thin file, but it has not created any blocks for it. So when you try to read from this thin file, it goes to this particular tree, and then it sees a lot of these blocks are unallocated. It just keeps on returning zeros. Okay, that is called as pre-allocation. So there are particular flags that are maintained in this inode, whether this block is filled or it is a holy file and all that kind of stuff. When you allocate it itself, you say that. And if it is in this particular mode, the file system can it can just create a buffer filled with the zeros and give it back to the user and say that this is what your basically file data is. It doesn't even have to go to the actual file system. Okay, so that trick is basically done. That's called a pre-allocation. Okay. The second thing is called delayed and multiple block allocation, which again comes as a part of the extent. Basically, what happens is when you do block allocations as of now inside the file system, they are done as a part of the write. As a part of the write, you go and actually do the block allocations. Here, the block allocations happens doing as a part of the page flush. The page flush is what happens when the pages are getting too filled. That's when the buffers actually getting written, right, to the actual hard disk. Although the blocks gets allocated as a part of the write, okay, the buffers gets actually written as a part of the page flush. Here, as a part of this delayed allocation, the block thing itself is got postponed to this because the guarantees are being given as a part of this pre-allocation, saying that your buffers, your size has been reserved for it. So because of this, basically what happens is you can have actually extras. You can have multiple blocks coming together. You can coalesce this together and then you can. So that's called as a delayed and multiple block. One more trick which has been given by EXT4. And checksumming has also been given. So this checksumming is basically general box also for more reliability to make sure that whenever you write to the checksum, each commit block will have a checksum that also gets written also, so that you compare it and the blocks are corrected. There's nothing can be done. There's no parity correction here. You can just flag saying that this commit is gone bad. Okay. So these are some reliability and performance things that have been given. So now coming to EXT4 on SSD. Now, because EXT4 does get a lot used on SSD, so along with regular hard drives also. So what are the pros of that? If people work on embedded devices, you should know that EXT has flash devices, something called the crib or the unmap operation. Basically, what happens is when you free a block on a hard disk, you really don't have to go and tell the this thing that I freed this particular block, because the block is just lying there. You just need to, and the next time you reuse the block, you just go and overwrite. But as far as flash is concerned, because like I told you about this var leveling and all that kind of stuff, the flash BIOS or the FTL needs to maintain when the file system is done using particular block. Basically, when you do a truncate of a particular file or you delete a file, you need to go and tell the flash file system, the FTL layer below, saying that, look, boss, I'm done with these particular blocks. I'm not using them anymore. Okay. So this has to be done by a particular operation which is called as an unmap. If you don't do this, it doesn't lead to correctness problem. It will just lead to a problem where the FTL thinks that these blocks are in use, but actually these blocks are not in use. So it leads to a whole set of, the whole flash works is it needs to have a bunch of free blocks always. And the flash performance degrades when the number of blocks becomes more and so at 50% flash, 30 to 40% flash performance is extremely good. Once it comes to 70%, it becomes bad. Once it hits the 90%, it becomes really, really good. But for disk, that's not a problem because it's a spinning thing only. It doesn't matter how much it's because this FTL layer has this problem. Flash really has to maintain how many actual free blocks are. But if the free block information is not maintained to the flash, sent to the flash layer, your flash can get degraded. So that is called something called a trim or an unmap operation, and that has to be sent to the flash. So EXT4 has a particular thread which you mount on SSD, and then you do this one particular mount option. If you turn this on, as and when the blocks gets freed, as far as the file system is concerned, this unmap thread will go on to the FTL saying that these blocks are actually free. Okay. Then there is supporting for different IO schedulers, database IO schedulers, which are basically deadline based rather than the regular electronic schedulers. So can attach them also. So that way you can have a good performance on EXT4. But actually the basic, there's a big con which I see on EXT4, which is also discussed on a lot of forums, is sequential IO really does not make sense for it. All this talk that we talked about, journaling, extents, is basically for sequential IO. Right? But actually Flash really does not do sequential IO. Flash is meant for random because it's like memory. Right? And how your actual physical blocks gets converted to logical blocks that only the FTL knows, no one knows. Suppose I can say that these are logical blocks which are sequential, right? But when I actually make an extent, they could be like spread out in various areas because the FTL does this conversion of logic into physical numbers. So whether all these performance guarantees that what you can see on a hard disk, you might really not see on a flash because the FTL could do away with bad FTL could just throw away all these performance guarantees. So even var leveling could redistribute the mapping. So that way, I would say that although EXT4 gets a lot used on embedded system and all that stuff, this is something that if you guys are working on embedded systems, you can watch out for. Okay. Now we'll go to a practical session. I'll just show you how the EXT4 gets this thing and the various modes, and then you can just do some file creation, style text and other stuff. Then you can dump the various EXT4 disk information. For that, I need to share my screen. Just for a second. Are you guys able to share screen? Are you guys able to see my screen?
Yes.
So here I have a VirtualBox image. I have basically not VirtualBox image. I'm running VirtualBox on my machine. And here if you see, I have one partition, one disk which I given, and I basically given it for running EXT4. Okay. So this I already created EXT4 file system using the nkfs command. Now I'll go to the list of comments and bit short on every RAM, so I have and all the comments. So first I'll mount it in which mode you guys wanted to mount it. First let us mount it in the order mode, which is the default mode. Okay. Or first we'll go to the write back mode. Like I told you, there are three modes. One is the write back mode, one is the order mode, and one is the full data mode, right? So the minimal time the journal takes is for the write back mode, where it writes only the metadata. Maximum time it takes is in the data journal mode, where it writes both the data and the metadata. And the order mode is writes to the metadata, provided it assumes that the data has been flushed to the hard disk. So first let us put it in the fastest mode, which is the write back mode. Let us do some IO on a file and see how much time it takes. I'm not doing any FIO or something on that. I'm just using the regular date command and see how much time it takes. Write a very big file. Okay. So do any of you guys know on VirtualBox how to copy? I have to type the command. No, not that copy. How do I copy paste?
In settings, you have to enable this copy options.
Machine setting. Machine setting.
Oh, you mean to say the original this settings? Oh, I never remember. User interface. Okay, I'll copy it now.
Use Control Shift V.
Control Shift V, yeah.
Control Shift. No.
You can click on input there, and then you can click on bidirectional copy in the menu above. Or a view, I'm not sure, but there should be some.
Yeah, there is some. I remember a long
yeah.
time saying it's bidirectional. Okay, let me just copy it. So be short on time. So mount -2 EXT4 -4. Once I copy, once I can just data is right back. So you receive a D message, it will say it is being mounted to the file system, the write back data. Okay. Now I'll do a small DD of one particular file, with a big count of 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. Okay. And we will do 5. 6 will be too much. Okay. Date. Just started at 31.5 seconds. Let's see. So it has taken 6 seconds. Okay. And I will put it as ordered. Then I'm just for safety seconds. It has taken 6 seconds, a bit more. Okay. Not too much. Now I'll put it in the What mode is that? Write back. Full mode. Data to the journal. This will take a lot of time. Okay, it's taking more than 6 seconds to put in on this, right? So this kind of tells the performance degradation of this. So fastest is write back, then the order, and then this. Okay. I'll just now let us try to look at some on this data structures. Okay. On this view again. So first, let us start with the super block. Okay. Key2 first and set that. So if you see, these are the various file system features that you have. Has journal, EXT attributes. So these are extended attributes. Extended attributes are actually started have from EXT2 they have is nothing but a registry that is maintained by the file system on behalf of the user. You can fill whatever nonsense you want to. Sometimes it puts it as a part of the inode itself, and if the registry grows big, it allocates data blocks for the extra. Okay, and EXT attributes gets used in a whole set of people who use mount these file systems on Fuse, for example, user-based file system. They use a lot of these external attributes for maintaining their own information. Okay, it's very useful actually. On a per file, you can put whole set of registry details, or even AC Linux for ACLs and all the stuff they use. Resize inode. This is a case where you can resize the file system. By the if you suppose you're going to have more partition grows, then you can resize. I don't know what's the reason that resize inode, but this is a mechanism by which you can resize your file system itself. Dir index is like this is actually comes as a part of the B plus tree for files, because directory is also a file. So you can have your directory itself also built as a B plus tree, so you can do a quick search of directory. Then recovery extent, that's 64-bit. I'll come to something called the flex block groups, super sparse, large file, huge files, uninitialized block groups, and all filled with zeros. So these are all the various features as far as this is concerned. An important thing, I think someone asked, where is the someone asked where is the journal inode? See, the journal inode is 8. So the journal itself is maintained as a file within this particular thing, which is having the file. You cannot. It's not only a hidden file. You cannot even see contents of the journal. Only can dump the disk block contents of the journal, which we'll do that now. So if you look at this, see, it has a block count of this, and it has something called, like I said, it has something called as a blocks per group 32768. So this block count divided by this blocks per group will give you the total number of block groups. I told you with the block groups, right? They are nothing but bunch of blocks which are partitioned together, right? That's nothing but block count. This EXT4 also has something called the flex block group that you see here. The flex block group is nothing but you have 16 of these block groups which are again coupled together. So they kind of write the super block information, inode information of the 16 block groups in the 0th block. So it's kind of not only you are partitioning your entire blocks into block group, you are clumping your block groups into this thing called flex block group to kind of replicate data, so that if some block group fails or something, you can go to another block group data. So this is mainly that for redundancy. Okay? That is one extra feature which I'm sure all of us will forget after this class, but that is given by this EXT4. So these are some useful information here. Now let us try to see the contents of the journal itself. So let us say we want to read this.
So basically, the journal can grow as long as it has the file system has space.
I think so. The journal block device maintains a cap of that. It's maintained, so it can grow as much as it can. And so I really don't know what is the key representation of the journal. Is it going to be this expense based, or is it going to be the block based? That also I don't know, because all that is written by the JB. So debug affairs. So I'm just trying to dump the contents of the journal. This will do a stat of it. Stat 8. Stat X. Attempt to read this block and then short read or open file system. I never seen this earlier. Okay.
File system not open, so it's not also mounted, right?
No, this is I'm just reading from the. It's not matter actually. Okay. Resulted in short read while open system. Okay. I don't know something. Let me just go.
Is it not dev STB one? You have given temp
Oh,
STB one.
yeah. What is this? Stupid of me. Okay. Okay. Now what I'll do is I'll just do some IO. Just mute it and write back. You can look at the contents of journal. So here you see it has created. So this is a journal, right? It has all this information here, and access time, blah blah blah. Everything's here. Important point is the extent. So here you see this is also maintain extent information. It has created one extent of this particular block, from 0 to 3 to 76, and from 3 to 76 it has created one particular thing. Okay, so many blocks have been created for one. It gives them this is the maximum thing for this thing, and then it's created this. Okay, actually we can see this from a regular file. Let us see how a file grows. Okay, let us try to create a sparse file and see how the extents gets done. Okay, for that I have this particular thing. State. Let us create a sparse file and see how the extent is. Suppose I'm just going to create 1000 files. Some file T2. This minus slides 10 minutes T2. It's 13. So if I do 13, for 1000 files here, if you see, it has maintained only one extent. So someone asked how a extent this information is maintained. See, only one extent information is maintained, saying from block number 0 to 1000, there are going to be 1000 blocks, and these are the physical block numbers. Okay. Now let us try to do one thing. Let us try to create a sparse file. So I will do an seek. Seek will create a big hole in the output file. So I'll create a big seek. Okay. So basically what I'm doing is I'm writing 1000 files at the beginning, I'm writing 1000 files at the end. Oh, sorry, 1000 blocks at the beginning, 1000 blocks at the end, and between everything is holes. Okay. Oh, sometimes it's very caches. Okay. So here you see, right, now because the debug FS was caching information, you can see clearly how extents are so beautiful. From 0 offset, it's created this from some huge block numbers. So only this two information is there in the metadata. No other information is there in the metadata. So with this, I created two extents, one at the beginning, one at the end, and everything else is 0. So if I use that, allocate command, and it create a thin file, if I read on any of this, it return zeros. So the file system will take care even before going to the file system, before even going to the hard disk. So that way the performance is so much better, right? I think so. With this, I would want to conclude. I think so. We'll see a bit of demonstration also. So, any more questions?
So the number of inodes is fixed, right, in a given file system? Or?
No, so this EXT4 allows, I think so, there's an optimization that done, something called a large inode. Previously, the inode number was capped some 2 to the power of 32 or something. Now they have a number of inodes, it goes to one more level. So they keep on block, which uses a hashing for mapping a logical to physical inode number. So you can have more number of inodes than 2 to the power of 32. And so you can convert inode numbers which are greater than 2 to the power of 32 to a different inode number, and there are mechanism to do that. That's a part of the EXT4 file system. With that, they are able to scale up to more than 2 to the power of 32 inodes.
Okay. Sir, one small doubt. Can you go to the code once? In that you have shown the extend blocks 0 to 999.
Yeah, sure. Yeah.
Yeah, this one. So does this mean 532, 512, 2, 533, 511? These many number of blocks are there, or only just these two blocks are allocated?
No. These many number of blocks. This is 512 to 5. These are physical blocks.
Okay, so that means there are so many, right? I mean,
there are so many. There are so many. Yeah.
1,000 blocks.
There are 1,000 blocks. So here, if you see exactly, there are 1,000 blocks. So this is so as far as the information is kept in the extent, it will have, so this tree, what I told you, right there, the tree, right, what I showed you, right, will have two entries only. One entry showing offset 0, one is showing offset this blah blah 10 to the power of 6. And each of these offset data payload will be 1,000 because there are 1,000 contiguous blocks. And the starting of the first block, 533, 512 in one case, and this 157. That's the only thing. Is that clear?
Yes, sir. I mean, I still didn't understand. Like, I mean, how are these showing in the tree structure?
I can just show it. I can just put a. So your tree will be something like this. Suppose these are the leaves. You'll have only two leaves, offset equal to 0, blocks equal to 1,000, starting physical block equal to this 532, 512, 532, 512. Okay, and there will be another leaf here. Offset equal to this 10 to the power of 6. Equal to 1,000. Physical block. Starting block equal to this. For this 1507. So your tree is only this, and maybe the root guy will point to this. So the top guy will have one indirect pointer here that will say offset equal to 0. Okay. Sorry, it will have 0. That's all it requires. Okay, because 0 less than 0 will be pointed to this, greater than 0 will be pointed to this. So it will have 2 pointers from here to here. And the leaves will just have this 2 information.
Yes, sir. Understood. Okay.
Okay.
Yes. Sir.
Okay. Any other doubts?
Does EXT4 support snapshots? Can you take a snapshot of a file?
No, there's no way, right? Because how can you have you need to have the copy on write architecture for snapshots. There's no way to. You can manually maybe do some without that can be done externally. It's architecturally not there inside the file system.
The architecture, yeah, nobody's hacked it.
No, a lot of file systems have nowadays.
Correct. I get that. No, but see, in UFS we had snapshots. I was just wondering.
Yeah, maybe that architecturally had it. Kind of had it. So basically, for snapshot, you need to maintain physical to logical block mappings. It needs to be done outside the file system. If it does that, you can do snapshots. This guy doesn't.
Yes. Okay.
Okay, any more doubts? Okay, then I think so we can wrap the session. I would be very happy if you guys can pass your feedback, what you found good, what you do not find good, so that in case Linux Kernel Foundation gives me an opportunity to present once more, I can take that into account and make those changes. Otherwise, I think so. Yeah, LVM solution. So I hope this was a informative session to you guys. I'm looking forward to more sessions. Okay? Thank you. I'm disconnecting. And if you got any doubts, you can pass the information and I can route it via the ATF. Okay. Thank you.